Good morning, students. Today we are going for the theory class of certain derivations. Here we have heat transfer, that is, we are dealing with the derivation to how to solve the problems, finite element problems when heat is transferred. So heat transfer, we know that F, the force factor F equal to EA alpha delta T 1 minus 1, where alpha is coefficient of thermal expansion. Coefficient of thermal expansion means how the shape of an object changes when the temperature is rising or varying. That is what we call as coefficient of thermal expansion. And in if F equal to E A alpha delta T 1 minus 1, the stress sigma equal to E dy by dx minus E alpha delta T. You know E is Young's modulus, A is area, and sigma 1 will be E1 U2 minus U1 divided by L1 minus E alpha E1 alpha 1 delta T. And now we can go for the derivation of stiffness matrix for one-dimensional heat conduction element. We all know what heat conduction is. Actually, heat conduction is transferring of heat throughout the element. That is, if heat is applied in this node, if the transfer of heat is only through this element, that is what we call as heat conduction. And we know the equation for stiffness matrix equal to B transpose B d dV, where B transpose is strain displacement matrix. And here D equal to thermal conductivity, that is rate at which heat passes through specific elements, that is how much speed it will take for the heat to transfer through this element, here this element, that is what we call as thermal conductivity, and it is denoted by small letter K, and its unit is watt per meter Kelvin. And here there's another change. In the previous derivations we had studied about shape function, and it's coming in here also. Here T, the temperature T equal to N1 T1 plus N2 T2, and N1 is same, that is 1 minus x by L and x by L. And we know that strain displacement matrix B equal to dN1 by dN1 by dx, dN2 by dx, and we are applying N1 and N2 in here, and we'll get it as minus 1 by L and 1 by L. Now we are substituting the B value in this stiffness matrix equation. So we will get 0 to L minus 1 by L, 1 by L, minus 1 by L, 1 by L, K, thermal conductivity K into dV, and we are converting, making this dV as area into height, area into dx, and we are multiplying B transpose and B. We will get 1 by L square minus 1 by L square minus 1 by L square 1 by L square, and here this is a constant term, sorry, Ka. Since 1 by L square minus 1 by L square is a constant term, we are integrating dx. This is the only thing that is changing. So while integrating, we will get, and by substituting the upper limit and lower limit, we will get it as L. So AKL 1 by L square minus 1 by L square minus 1 by L square 1 by L square, and we will get thermal conductivity, the stiffness matrix of conduction, if heat is conduction, as AK by L 1 minus 1 minus 1 1. This is the equation for stiffness matrix if only conduction is there. I repeat, if only conduction is there. And finite element equation for one-dimensional heat conduction, that is force factor. And we know that F equal to K into T, and here force factor F equal to thermal conductivity, stiffness matrix of conduction into temperature. In previous we have studied that force factor equal to stiffness matrix into displacement matrix, and here it changes to stiffness matrix into temperature matrix. That's the only difference. It is almost similar. The equations are almost similar, and here we can write it as F1 F2 AK by L 1 minus 1 minus 1 T1 T2. And now we are making certain changes in the situations. That is, finite element equation of one-dimensional heat conduction with free end. We are considering another term, free end. So while considering a free end, there's a chance for convection also. That is, if we are taking this element which is sealed in here and the two nodes 1 and 2, and heat is passing through here, this node, and throughout this element conduction will occur. And I already repeat what conduction is. That is, transferring of heat throughout the element is called as conduction. And beyond this point, beyond this boundary, convection occurs. And what is convection? Actually, the term convection means the transfer of heat from one medium into another medium. In our case, the heat is transferring from this solid body to the atmosphere. So this T infinity means heat, the temperature of atmosphere or temperature of the air in that specific area. And we already know the stiffness matrix while conduction, that is throughout this material, is AK by L, 1 minus 1 minus 1 1. And we want to know the stiffness matrix while convection. For that, there is an equation KH. We are considering KC as stiffness matrix for conduction and KH as stiffness matrix for convection, equal to integral H n transpose n dA, where H is heat transfer coefficient. And we know n1 and n2 as 1 minus x by L and n2 equal to x by L, and we are applying boundary condition. For node 1, here node 1, x equal to 0. While applying the x value of 0 in here, what we will get as 0 by L is infinity, 1 minus infinity, which is n1 equal to infinity. And for node n2, here n2 is in here, so x will be L by L equal to 1, and we are considering this infinity as 0. So we will get KH equal to integral H 01 dA. And now we are multiplying these two, so we get 0001 H, and we are integrating dA with respect to A, and we will get A. And this is the equation for stiffness matrix when convection occurs. And to find out the stiffness of this entire process, we want to multiply stiffness matrix by conduction plus stiffness matrix by convection at end. We want to note at end, because while applying the boundary condition, the whole equation will change. If certain other conditions occurs in questions, you want to read the questions clearly to find out the equation, and we are substituting both the values of KH and KC. Thank you. If you have any doubt in the derivation, please call me or WhatsApp me.